The purpose of this experiment is to observe and determine the magnetic fields produced from a powerful magnet at various observation locations and to quantify its magnetic dipole moment. The models used in this experiment were a neodymium magnet and a magnetometer sensor application on a mobile phone to assess the magnetic fields produced from the magnet. The fundamental physical principles used in the experiment were the Biot-Savart law and the magnetic fields production from a magnet and the Earth. The overall result of this lab was that the calculated magnetic field from the magnet at an off-axis observation point from the experiment almost resembled the calculated value from the coded model. The magnetic dipole moment was also assessed to be 3.63 amperes square meters. Before observing the experiment, here are the fundamental equations and principles. The Biot-Savart law defines the magnetic fields produced from a current, and this relation is further applied to magnets as a magnetic dipole. The Biot-Savart law is defined in this first formula, which defines the fields using the magnetic dipole and the position vector from the observation point. When the magnetic dipole is parallel or antiparallel to the observation point, the formula simplifies to the second equation. Similarly, when the observation point is perpendicular to the magnetic dipole source, this third formula is used. This second relationship was also used to quantify the magnetic fields in relation to the distance to the source, and this value was used to determine the magnetic dipole and the Biot-Savart law. The reason for why the neodymium magnet was used as the model in this experiment was because it possesses a powerful magnetic field that could interact with the Earth's magnetic field at the observation point from the magnetometer. The assumption was that the magnet would act as a magnetic dipole, and this further explains the use of the Biot-Savart law to calculate the field and the dipole. The system of this experiment is a magnetometer sensor, and the surroundings is the rest, which includes the magnet, the Earth, and any interferences with the magnetic fields. The initial condition of the experiment was the isolated magnetometer that only interacted with the Earth's magnetic field. The experiment involved the measurement of the magnetic fields produced from the magnet by placing the magnet on an axis to the sensor assessed by the Physics Toolbox magnetometer app and aligning the sensor to make the Earth's magnetic field on it to be 0. The distance of the magnetic field values were plotted in a logarithm graph to determine the distance dependence with the magnet, and this slope and equation was used to calculate the magnet's dipole moment using the distance relationship and the K constant. The experiment also determined the magnetic field from the magnet at a position that is off-axis to the magnet, which is this last line right here, and this value was calculated experimentally and using a coded model as well. When the magnetometer was placed so that the X component had no interactions with the Earth's magnetic field, observations 1 and 4 were observed, showing that the further the distance from the source, the smaller the magnetic field observed, and vice versa. The code first created a function that calculated magnetic fields based on the Biot-Savart law, which is defined in line 31 of this code. Then, 2 observation points on axis and 4 on the perpendicular axis were set at a defined distance, which was determined experimentally when the magnitude of the magnetic field was 100, which was 0.191 meters. These positions were used as the position vectors to calculate a magnetic field vector using the Biot-Savart function defined in the previous slide. This calculation was done for all arrows in the parallel and perpendicular positions. This calculation was also repeated for the off-axis calculation for this position vector in line 110, which is 45 degrees from the magnet. The output of this code shows the direction of the magnetic fields at the parallel with the orange vectors and the perpendicular, the blue vectors, distances from the magnetic dipole, as well as the 45-degree off-axis position. The calculated magnitude of the magnetic field off-axis was also an output of this code, which is 2.897 times 10 to the negative 5 teslas. The main similarity and difference between the model and the actual experiment was the calculated value for the magnetic fields observed at an off-axis observation point. The experiment calculated the value to be 5.359 times 10 to the negative 5 teslas on the Excel file, while the code calculated it to be 2.897 times 10 to the negative 5 teslas, which is slightly lower than the experimental value. Some possible sources of error that could have accounted for this could have been the human error involved in measuring the magnetic fields produced from the magnet, as the alignment may not have been exactly 45 degrees from the magnet, which could have altered the distance to the magnet as well as the interaction with the Earth's magnetic field. Also, external interactions with nearby electronic devices could have also impacted the experimental measurement. While The result of this experiment would have changed if the setup did not compensate for the magnetic north of the Earth, as the x component of the magnetic field at some intermediate angle would have both the magnetic fields from the magnet and the Earth. This would have made it extremely difficult to determine the magnetic fields solely from the magnet, causing the result to be skewed. When two magnets are stuck together, the magnetic fields will be stronger in the same direction as the magnet would exert a stronger magnetic dipole moment, thus increasing the magnetic field at the observation point. Thank you for your time in watching this video.